Welcome to our first lecture in theory of computation. So I'm going to introduce some terminologies about automata or theory of computation and also a short discussion about the history of automata. So what is the course goal or course objective in discussing our course? So we want to determine the capability and limitation of our computer. So we want to know how good a computer is in processing a certain task or doing a solution for a certain problem. Okay, so based on complexity theory, computability theory, and automata theory. If we say complexity theory, we are going to determine if some problems are hard to be computed by our computers, or is this easy to be computed? While computability theory is all about can it be solved by a computer or it cannot be solved by the computer. While automata theory is how can we mathematically model computation? How can we derive a mathematical equation or how we're going to present that process in a mathematical domain? Okay, so let's define what is automata theory. So automata theory is basically a study of abstract computing device or machine. So if say abstract, this is a theoretical, okay, theoretical computing device. It could be in a paper or a simple design in a paper, okay, or it's a simulator in your software, okay. So basically, we have a theoretical computing device that process our problems or our inputs. So this abstract computing device, we call it automaton. And again, device means it doesn't mean that we have a physical hardware. It could be a design that is written in a paper. Okay. And as a computer scientist, so we want to know the different models efficiency. Okay. What can it do? What cannot do? Okay. What is the limitation of the different models? And this study is basically the theory of computation. Okay. And again, in automata theory, we're going to compare computability versus complexity. Will it, if the problem is hard, okay, so what is the effect on the computability of that problem, or vice versa? Okay. So now let's move on with a brief discussion about the history of automata or theoretical theory of computation. So let's start with Alan Turing. So he is called the modern father of the modern computer science, a mathematician, and he's the one that created the Turing machine. If you still remember in our AI, we studied or we I introduced to you what is Turing machine. Okay, how does it work? And also, Turing test was introduced by Alan Turing. So this test is used to define how AI is can deceive the user, the people. Okay, if and that they could perceive that AI could perceive that he's a person or it is a person. Okay. So this is an example of a Turing machine wherein all processes is stored in this tape. Okay, the step-by-step processing are stored in this tape. So it includes the input, the rules in processing, and then the output. Okay, so aside from Turing or Alan Turing, okay, so in 1940s and 1950s, so finite automata was being studied. So one of the scientists that studied finite automata is Noam Chomsky. So he proposed Chomsky hierarchy for the formal languages. Okay, so it will be discussed on Module 2. And in 1969, Cook introduced intractable problems or NP-hard problems. And then in 1970, modern computer science, compilers, computation, and complexity evolved since a computer evolved from the Jurassic to a new technology. Okay, and aside from them, we also have this famous scientist and mathematician. So we have George Cantor that discuss theory of sets, okay, wherein it is used in designing our automaton. And we have David Hilbert, algorithm and rules of inference, so definitely for AI. And Kurt Gödel, so incompleteness theorem. So a true statement without any possible proof. You still remember in um in discrete math we discussed there are some statement that is considered as true. Okay. And also Church, Stephen Colclean, and Emil Post. So they said that there are some problems cannot be solved. There's no algorithm that can solve these problems. Okay, or some problems cannot be computed. Okay, so now let's have a review about sets, multi-sets, and sequence. So we already discussed this in CS 137 in our discrete math. So what is a set? So order and repetition don't matter. So for example, we have a set that contains 7473 is equivalent to a set that contains 347. So two of sevens is just considered as 1 7, and the order doesn't mean anything. You could change the order, still you have the same set. While for multi-set, order doesn't matter, but the repetition does. So you cannot remove an element on multi-set because if you're going to remove it, okay, it it will not be equivalent to the original multi-set. So for example, we have 7473. If we want to arrange this order and the order of our elements, it's okay. It will still be the same. So 3477. But if we're going to remove the redundant 7, now it will not be equal to the original multi-set. Okay. And for sequence, order and repetition matter. You cannot change the order. You cannot remove a certain element in sequence because they are defined by their relationship with the other elements or based on a formula to define the different elements in the sequence. Okay, so that's why we cannot remove or alter the order. So that's set, multi-set, and sequence. And also in discrete math, we discussed set notation. So these are the functions that we use in sets. So we have union, intersection, complement, Cartesian, and power set. If say union, so we are combining all elements of A and B. So for example, we have A that contains 1, 2, B contains 2, 3, and our universal set is X is an element of natural number where E and X is less than 6. So it means the universe is from 1 to 5 only. So if we have A union 5 and A union B rather, so we're going to combine all elements of A, B. So now we have a set that contains 1, 2, 3. And if we're talking about intersect, we are defining what is common between the given set. So A intersect B, common 2. And if we're talking about not negation, so A not means disregarding the elements of A, okay, in the universe, okay, disregarding, and the rest will be part of that negation. So since our universe is 1, 2, 3, 4, 5, so removing 1, 2, we have 3, 4, 5 as the not. And if we are talking about Cartesian, so basically we're just going to um, match an element of a set to the element of the second set. So for example, we have 1, 2, 1, 3, 2, 2, and 2, 3. And don't forget, in the Cartesian product, we cannot change or alter the order of our values inside the parentheses. Why? Because the first value refers to A and second value refers to B. So therefore, if you're going to make 1, 2, 2, 2, 1, now the value of A and B will change, which is not equal to the original AB. Okay. And if we are talking about power set, we are referring to the subset that we could obtain on a given set. So what is the power set of A? So using the power of 2 rule, 2 raised to n, wherein n is the number of elements. So 2 raised to 2, 4. So we have 4 subset in power set of A. So it starts with a null, and then first subset contains the first element, third subset contains the second element, and the fourth subset contains all elements. So that will be our power set. So I hope you still remember this, the different functions that we've discussed in discrete math and some terminologies, because we're going to use it here in automata or theory of computation. Okay, now let's discuss what is a function. So basically, a function is a way of mapping one value in a set to another set. This function is a rule to define that relationship. Okay, so the first set wherein we get the input for that function, we call it the domain. Set containing all possible output values, okay, on the second set is called range. So for example, we have this n. These are the inputs 1, 2, 3, 4. The function at n, so basically we have a formula or a relationship with n. Okay, so we have these values 2, 4, 2, 4. So if we're talking about the range, this will be the result. So 2, 4 is the range for the output. While if we're talking about the domain, so the possible input values are 1, 2, 3, 4. Okay, so this is the domain 1, 2, 3, 4, and the range is 2, 4. Now, let's move on with the relation. So if you still remember, in discrete math, we discussed predicate. So we create a function intended for a member of a group or for a group that could be either true or false. Okay, and relation. So this an example of this relation is basically the output of the Cartesian product. Okay, wherein one value is related to another value. Okay, so some properties of relation. So we have reflexive, irreflexive, transitive, symmetric, and asymmetric. So how could we determine if it's a reflexive, irreflexive, or asymmetric? So let's have this example. So using equal, less than, or equal. So equal is reflexive if two values are equal. So 2 equal to 2. They are reflexive. So that's why A relation A is true, therefore it's reflexive. Okay, but in case if they are not equal, okay, it's reflexive. So 2 less than 3 is not equal, so implies 2 not equal to 3, so irreflexive. If say symmetric, x equals to 2 implies 2 equal to x. Okay, so you could change or alter the direction, not direction, the order of our values. Okay, and still they are equal. So A is equal to 2, 2 equals to A. X equals to 2, 2 equals to X. Okay, and if say transitive, okay, so we have 2 less than, relationship, 2 less than 3, and 3 less than 5. through 3, we could say that 2 less than 5. So that's transitive. So it means we are transferring the relationship from 3 to 2. And we say it anything less than 3 will be less than 5. Okay. And for antisymmetric or asymmetric, okay, so it means when we change the order of the relationship, okay, it will be false. So for example, x less than or equal to y and y less than equals to x. So if we're going to change it, it will become false. Okay. And also in discrete math and in artificial intelligence, we discuss graphs. So these are collection of nodes and branches. Okay. So what is node? Basically this circle. So if we're going to relate it to automata, this will be the phases of the process or the states of the process. Okay. While the connecting lines, what I have said, this is your edges or your branches. It connects the nodes. It defines where to go within the graph. Okay. Or what nodes are connected. And also, we discuss in AI, in graph, we define the degrees. If say degrees, the number of nodes connected to one node. So if we're referring to this node, this is degree 1 since we only have one node. But if we're referring to this node, it is degree equal to 2 since two nodes are connected to it. 1, 2. And for this node, the degree is 3 because 1, 2, 3 nodes connected to this node. Okay. And this node or this graph rather is considered binary tree. Why? Because we have two branches or two edges connected to one node. 1, 2. To this node, 1, 2. And also in the graph, we could consider part of the graph when we discuss it, when we analyze it. And that part of the graph, we call it subgraph. Okay. So in this example, this is the subgraph. These 3 nodes, part of these 5 nodes. Okay. And we also have direct graphs wherein the edges have directions. If still remember, in AI, we discussed the shortest path wherein the edges has arrow. Arrow means the path where to go, what is the start and what is the end state. So in this example, the direction will be 2, 1, 3, 1, 4, 3, and 5, 2. Okay. And into automata, okay, so define the values that will be processed is based on this hierarchy. So let's discuss languages and grammars. So if the input has no string, no string, but no length, okay, we call it an empty string. And this is the symbol for that epsilon. So there's no symbol on that string. So nothing. Okay. And if we are referring to the symbols used to represent our input, we call it alphabet. So for example, 0, 1. And the collection of alphabet to form a certain word or strings. Okay. And the collection of words or strings, we call it languages or language. And to define how language or the different synthesized word strings to form how they are connected, how they are to form a good language, okay, call it grammar. Okay. And this language and grammar again is was studied by Chomsky. Okay. And going back to discrete math, we discussed Boolean logic, the conjunction, disjunction, negation, exclusive or, and equality. So conjunction, uh, at least one of the input is false, automatic that's the output is false. Disjunction, if there is a true input, the statement will be true, the output will be true. Negation, true will become false, false will become true. Exclusive or, the input should have the same have different values to have an output of one. Equality, implication. So we already discussed this in proving if a certain statement are equivalent or not. Okay, yung equality natin. In implication, we studied this in if and else statement natin. Okay, and also we discussed proof techniques. So we have construction, contradiction, and induction. So for construction, this method, the example of this method is the direct and indirect method. While for contradiction, we're going to find a value that will make the statement false. If we cannot find, the statement is true. While for induction, this is used to um, define if the mathematical equation that involves natural number is true or false. We're going to prove it beyond the limit of that, beyond the limit wherein the equation will be true. So if the upper limit is k, we're going to prove that equation beyond k, which is k plus 1. Okay, so let's have this example. We're going to prove that 2 is equal to 1 based on what we have discussed in discrete math. So prove that 2 is equal to 1. So consider the equation a is equal to b in proving 2 is equal. So multiply both sides by a to obtain a squared. This should be a squared is equal to ab. Okay, a times a equal to a times b. So based on this, they are still equal. And then you subtract b squared again to both sides. So it means they are still equal. A squared minus b squared is equal to ab minus b squared. Then we factor. So left side will be a plus b times a minus b, while the other side is b times a minus b. And then solve for b or a. So we divide both sides by a minus b. Okay, then we get a plus b is equal to b. If b is equal to 1, 1 plus 1 is equal to 1. So therefore, they are equal. Is this correct? Is this a fallacy? Is there incorrect analysis on this proving? Which line? For this problem, definitely this is a fallacy. There is a line which is incorrect, which is this part, wherein we divide a minus b to both sides. Why? If they are equal, if a is equal to b, therefore we're going to have division by 0. If we have division by 0, therefore the result is undetermined. Okay, we cannot have a numerical output. So we forgot there is a value that will make this statement incorrect, which is a minus b equal to 0. Okay, so based on that, this second and last step will be invalid based on the a minus b equal to 0. So therefore, this proving is a fallacy. Okay, so I hope you still remember our discrete math and our AI. Okay, so kindly review and Thank you for listening. See you on the next video lecture. Thank you.